Okay, so let's continue. Okay, so we're going to take linear functions for which we all use the same partial of capital F. Okay, so let's keep this picture for a while. Okay, remember that this picture corresponds to what's going on here. Now I erase this. Yeah, so the orange lines here were the linear approximations, and the first one was the one that started in 0. So now let's write the other linear function, so not the one that Newton uses, but the one that uses the partial derivative in this point. Okay, so I'm looking at, I start in the origin, and my value in the origin that I start with is the value of f in the origin. So I start with f of x in y0, which is 0. And then I'm looking at the linear function, which has a linear part determined by the partial of f with respect to y, and this acts on y. Okay, so that's not this orange function here, not the function which has this orange graph here, but it's the function that starts with the value of f in the origin, in y is equal to 0, x is a parameter, and the linear part is given by the partial of f with respect to y in x and y equal to 0 acting on y. Which means that my okay, so this is my starting value for y, so y0, y0 is equal to 0, and I put this equal to 0 and solve for y. Okay, so that's not this y1, it's another y. Okay, so this is the orange y, and this is going to give me, this is in white again. So I put this equal to 0, so then y1 is defined by y1 is f. This goes to the other side, so this is f y0, 0 inverse acting on f of f and x equal to 0. Okay, so that's y1 and this is y0. And yeah, if I think of in terms of my window, x, y, and some window here, okay, in x and in y, which I still have to choose because it's not going to work for any window. I will probably have to take this window sufficiently small. Then how big can this be? This is y1. It's defined in terms of this fixed inverse of this partial derivative acting on f of x and 0. Okay, so if I want my window here to contain, yeah, so I start here with for some x with y0, and this defines me a y1, which depends on this x, of course. And this part, Okay, y1 I get by letting this act on this, and this plus or minus doesn't really affect how large y1 can be. So it's clear that this should not be too large. Okay, now this not being too large, okay, I know that f of 0 and 0 is 0. Okay, so for y1 to be contained in this window under consideration, I still have to choose. In the y window, yeah, my y window is an estimate on y, how big it can be, over here and over here. Yeah, it has to be between these two. To be contained in the y window, for y1 to be contained in this y window that we still have to choose, f of x and 0 should not be too large. Okay, and since f of 0 and 0 is equal to 0, this is really something that has to do with the continuity. This relates. Okay. Okay. So this can be established by using the continuity. The continuity of x going to f of x and 0. Okay, f of 0 and 0 is 0. So if this thing is continuous, then I can choose x small to keep f minus f of 0, so that's effectively f of x and 0, to keep f of x and 0 small. Okay, so if I specify my y window, I can use the continuity to make my x window sufficiently small to keep this small. Okay, and then, okay, so this is small, and then this thing acts on it. So, using the continuity, I can make sure that this y1 is in some window that I still have to specify. So the continuity of x going to f of x and 0, together with the fact that this is fixed, allows me to narrow down my x window in such a way that y1 will be in this window for y. Okay, so we will have to make that precise later, but let's first look at the second step. The second step. Okay, so now I've computed some y1. In this picture it's not this y1, it's probably this y, it could be this y1, because I've taken a different linear function that I intersected with the y-axis. Yeah, so this y function is this y function as a function of y. Okay, I've put it equal to 0, and that gives me my first iterate y1. Okay, and now I repeat the trick. So at this point, I look at the curve, I look at the graph of f, and then I take a linear function which is equal to, which in y1 has this value, okay, but I give it the same coefficient. Okay, so my, yeah, so in this picture it's going to be this one over here. Okay, and I immediately see that this method is not obviously going to give me a convergent sequence of iterates, because my next y2 is going to be here. So without additional assumptions, it's not clear at all that that y2 is compared. Okay, I started in the origin with y0 is equal to 0, gave me y1, gave me y2, okay, and then the next one is y2, y3, So a priori it's not so clear that this is well behaved. Okay, so we have to put some additional information, use some additional information to make it well behaved. And therefore, to do that, I first look at the formula for y2. So how do I get y2? I take my x is a parameter, I start in y1, then I use the same derivative, okay, and then, okay, I'm in this point, okay, so now here I have to put y minus y1, okay. That's my formula for the function which has this white line as a graph. Now remember that this was still z. Okay, so I put this equal to 0. And then I solve it. And now I see that if I solve it, I have to put this to the other side again. Okay, there's enough space here to write it. So now I put this to the other side again. And then I get y, okay, so then I solve and the solution is called y2. Okay, so that's going to be y2 minus y1 is something, but I put the y1 on the other side. y1, and then I just copy what's over here, fy0 inverse, this was y0. And now this acts on f of x and y1. Okay, and with two okay, the first step is a bit different from the second step, but with the second step it's clear what will be the third step. In the third step, this is going to be a 2, this is going to be a 2, and this is going to be a 3. Okay, and now the idea is that, okay, if I have my y1 which is controlled by this function here, then I can try to look at y2, okay, I can try to estimate y2 using this formula, but I can also subtract these two and try to estimate the difference of y2 and y1. So let's look not at how large y2 can be, but let's look at how large the difference of y2 and y1 can be. Okay. The difference of y2 and y1. Okay, and then the difference of y3 and y2. Yeah. So let me write down y3 minus y2 to get the general picture right. Yeah. So this we know. This we can copy later. So here I put y3 is y2 minus f by 0, 0 inverse acting on f of x y2. Okay, so the reason for putting this one is that this one is a bit exceptional because I didn't put anything here. So to see that everything is really the same, it's better to put y0 is 0 here. Okay, here y0. Now it's clear that this, and this. You see y1 is y0, y2 is y1, y3 is y2. So now I can subtract two of these to estimate the increments. So I can estimate the increment from y1 to y2, and then I subtract these two, and I can estimate the increment from y2 to y3, then I subtract these two. And maybe it's more instructive to, because this one is a little bit exceptional, because this 0 here, maybe it's a bit more clear if we just estimate y3 minus y2 to get the general picture right. Okay. Yeah? Now, I don't need this. Yeah, so we have in mind what this picture is, and now we forget the pictures and we just do the estimates. We just do the estimates for the increments. So estimate the increments, so y1 minus y0, y2 minus y1, y3 minus y2, etc. Yeah, and let's do this one to get straight what's going on. So y3 minus y2 is equal to y2 minus y1. And then I have minus f y 0, 0 inverse acting on f minus f, but this is in y2 and this is in y1. F of x y2 minus f of x in y1. That's my increment. Okay, so here's the difference of y3 and y2, y2 and y1, and this also has to do with the difference of y2 and y1. Because it's for the same x, the difference of a function in y2 and y1. Okay, so equal to so there's this inverse of the coefficient of the linear term. And now you can, okay, so the trick that you could sort of think of is that you take this outside. Okay, so I take this outside, inverse, then I have large opening brackets, and then this is outside, so the f minus f is going to be here, but then this here, okay, I took it outside, there was nothing there, so I put y2 minus y1, and then here I have minus, this is gone, so this is f x y2 minus f of x minus y1, closing bracket, another closing bracket. The difference of two function values and the difference of two originals with a partial with respect to y, the variable here. Okay. Now this quantity here, this difference here, is the difference of two function values. So I can write, so let's concentrate on this part here. And now I'm going to use a theorem which is known as the Mean Value Theorem. And it has to do with an intermediate value for the derivative. Okay, you've probably seen that theorem. But I'm using a variant of this theorem. And the variant comes from doing a trick with integrals. And the trick with integrals is the following. That is that I write this difference here. Okay, there are many cases where you do this trick. So it's good to identify the trick and then make sure that you remember that you've seen it so that you can use it in other situations. I write this as f of x times t y2. If I